much. Hello everyone, my name is Cong. I'm a fourth year PhD student from University of Waterloo. In this talk, I'll walk you through my journey of designing compilers for lexical effect handlers. In the first few slides, I'll go over the background that you need to understand this talk. Effect handlers are a powerful language feature and subsumes many control flow features such as async await, coroutine, and generator. To demonstrate the power of effect handlers, here I present a program with user-level scheduling where two threads take turns to execute. We define a global variable parked, which stores the continuation of the dormant thread while the other is running. Work is where all the computation happens. We'll look at it shortly. The main part of the program consists of launching two threads. Now let's look inside work. It consists of a single handle with expression. The handle body does useful computation, which is not shown here, and it periodically raises yield effect to transfer control to the other thread. The handler contains the code that is executed when an effect is raised. The yield handler in particular contains a scheduling logic. Let's simplify it to look at the essence. The yield handler takes in a parameter k, standing for the leftover computation from the program point that raised the effect. This value is called continuation or resumption. Inside the yield handler, we first load the pair continuation from the global variable. Then we park the current continuation. Finally, we resume the pair computation. When this program runs, the two continuations take turns to execute. If you've never seen a continuation before, I hope that you find this example magical. Remember, traditionally, a scheduler like this has to be implemented by a runtime, like an operating system. Now, it can be built entirely within the programming language. Effect handler, though powerful, suffers from a modularity problem. In the next few slides, I'll walk through an example to illustrate this problem and show how recent work on lexical effect handler address this. Assuming you're an application developer, you import a plugin and framework from third-party libraries, and you invoke framework by instantiating the plugin. Now say you want to monitor the usage of plugin by the framework. You create a wrapper function that calls plugin and then raise a login effect. And you also install a login handler in your application. Now, since effect handler isn't mainstream yet, and most of you don't have experience programming with it, let me explain why the programmer would expect this to work. Programmer expect this to work because both the raise and handle with expression use the name login. And because the name appear in the same lexical scope, they would expect them to refer to the same thing. And why would a PL designer want this to work? Well, we build PLs to help programmers write modular and reusable softwares. In order to be reusable, the framework should be agnostic or polymorphic to the effect of the plugin. If we indeed have such a modular PL, then the framework is statically prohibited to do anything with the login effect of the wrapper. Only the program text that is aware of the login effect should handle the effect, which is right here. However, many works on effect handlers use a semantic that is not modular. When an effect is raised, it is handled by the closest handler on the stack. To see how such semantics could go wrong, let's assume that the framework that you imported install a handler for its own purpose. Of course, as the application developer, you do not know that. If you run this program, the login effect raised from plugin will be accidentally handled by the handler in the framework. This behavior makes it very difficult to reason about the program. For example, if you import a framework that does not install an enclosing login handler, then your application will work as expected. We know that this problem is similar to the abstraction problem with dynamically scoped variables, which has fallen out of favor since the 80s. From another angle, this is a problem with names. Both the application and framework use the same name, login, for their internal purpose, but it results in a name collision when the two modules are composed. Recent work has proposed lexical effect handlers as a promising alternative. In a language with lexical handlers, the handle with expression binds a name variable. When a lexical handler is installed, the runtime generates a fresh name for this handler. This name substitutes for the name variable inside the handler body. Here's another presentation for the same expression, which highlights the stack structure. The program has two stack frames, a handler frame at the top with name 314, followed by the current redux. This slide puts lexical semantics and traditional semantics side by side. We can see that with the lexical semantics, every handler is given a globally unique name when it is installed. the traditional semantics does not have such guarantee. Prior work have also formally shown that programs built with lexical effect handlers enjoy modularity. Now, my doctoral work focused on designing and implementing efficient compilers for lexical effect handlers. We introduced a high-level language Lexa and show how to compile high-level modular effect handlers into low-level Swift stack switching. I organized this talk around 3 pieces of work. Each solves a distinct problem centered around compilation. These 3 work expand the landscape of effect handler compilation and bring out interesting trade-offs between performance and expressivity. Furthermore, all techniques used in this work are formally proved correct. Let's look at the work which we call direct Lexa first. Direct Lexa is our first attempt at efficient compilation of lexical effect handlers. We start from the simple insight that handlers do not need an extra name because they already have one, which are their stack addresses. Using stack addresses as handler names has an extra benefit. When raising to a handler, originally we need to walk the stack to locate handlers with matching names. With stack address, this time it reduced to 01. Besides finding handler, an efficient implementation of effect handler also requires capturing and resuming continuation efficiently. Lexa achieves constant time continuation operation using a technique called stack switching. In the next few slides, we will see how stacks are laid out and how they're manipulated during effect handler operations. Stack switching consists of 3 phases: enter, raise, and resume. We'll look at them one at a time. Let's first look at what happens when we enter a handle with expression. The red arrow in the stack pointer pointing to the current stack. The handler in the handle with expression is installed on the bottom of a new stack in a structure which we call handler frame, highlighted in yellow. The handler frame contains a pointer field that points to the top of the prior stack. We call this field exchanger, and you will see why shortly. After the handler is installed, the handler computation will use the new stack for storing their local variables. Let's look at what happens during a race. The computation is currently inside 2 handlers, so you see a linked stack structure. Say that the current program point raises to handler 1. Raise requires capturing continuation, and this is done by simply exchanging the content of the exchanger and the stack pointer. After the exchange, the stack pointer points to the top of the previous stack, and the original stack pointer is stored in handler 1's frame. This effectively captures continuation, which can be resumed later. Resuming the continuation similarly involves an exchange between the exchanger and the stack pointer. After the exchange, the continuation becomes linked to the stack again, and the computation resumes from the top of the last stack. We implement the aforementioned design into the Lexa compiler. The core of the compiler is a library which we call StackTrack. It includes handwritten assemblies that carry out stack switching. Overall, the Lexa compiler first compiles high-level Lexa program into C, which is combined with the StackTrack library and sent to LLVM for further optimization and code generation. We compare the performance of Lexa with other programming languages with support for effect handlers. The results show that Lexa is not only fast in absolute terms, thanks to many of our low-level optimization, it also scales extremely well due to our design which makes raise and resume all 1, regardless of the shape of the stack. Next, let's talk about multi-Lexa. The example we've seen so far all use single-shot resumption. Multi-shot resumption are resumptions that are resumed multiple times and then bring extra expressive power. This slide presents a checkpointing program which takes in a program and runs it within a save and retry handler. The program can raise save effect to save its current continuation. After that, it can raise retry effect to discard the current computation and instead resume the saved continuation. Because the retry handler can be raised multiple times, the saved continuation also needs to be resumed multiple times. Although multi-shot resumption offers great expressive power, direct Lexa sacrifices it in favor of efficiency. To see why direct Lexa is incompatible with multi-shot resumption, let's see how direct Lexa implementation differs from the formal semantics of lexical effect handlers. The top of slides show the reduction step according to the formal semantics of lexical effect handlers. This configuration considers 3 handlers. the continuation consisting of handler 1 and 2 is captured and then copied. Notice that the copies of handler have the same name. Now, say that the current program point raised to handler 1, the operational semantics walk the stack and will correctly find the handler 1 on the active stack. In contrast, when resumptions are copied in direct Lexa, copies of the same handler will have different addresses. Although the current program point has a pointer to the original copy of handler 1, this address is useless to locate the correct copy on the active stack, which now has address 3. Because of this, direct Lexa simply aborts if a resumption is resumed more than once. In multi-Lexa, we add back multi-shell resumption, yet still retaining the performance edge of direct Lexa. Our technique borrows idea from virtual memory management, and we call it virtual resumption. In multi-Lexa, stacks and handlers live in virtual memory space, and all addresses are virtual addresses. For a given address, we call the higher bits zone number, middle bits handler ID, and the lower bits stack offset. Each continuation lives in a different zone, and copies of the same handler in different continuation live at the same relative address within the zone. See the example on the right. All 3 handlers initially live in zone 0. Say that we captured a resumption consisting of handler 1 and 2 and copied the resumption and resumed it. The stack diagram will look like this. A new zone is created to host the resumption, and handler with ID 1 and 2 are copied inside it. Notice that the copies of handler live in the address with the same handler ID as their original address. This enabled efficient address redirection, as we will see in the next slide. In multi-Lexa, when a program uses an address, a software-level memory management unit, SMMU, performs address translation. For instance, if a program raised to handler at address 020, control is transferred to the SSMU, which translates the address through the following steps. First, SMMU uses the current stack pointer to determine that the current zone is 1. It also uses the given handler address to determine that the target handler has ID 2. The SSMU performs a zone walk starting from zone 1. At each zone, SMMU checks if the zone contains a copy of the target handler. The check is surprisingly simple. We only need to compare the target handler ID with the ID of the first handler in the zone. If the target ID is greater or equal, which is the case here, then this zone must contain the target handler. This must seem very magical, and I agree. The reason why this simple check works relies on 2 important invariants. First, SMMU ensures that every stack are created with monotonically increasing handler ID. Second, the type system with lexical scoping put another structure invariant on the stack layout. I won't go into details due to the time constraints, but I'm happy to talk about it later. The check reveals that zone 1 indeed contains a handler with ID 1. Next, the SMMU modified the given address 020 to 120, where the zone number is replaced by the zone number that the zone walk ends up in. Finally, SMMU returned the translated address 120 to the program, and you can check that the handler at 120 indeed exists and is a desired handler. We implement SMMU as a library that provides an API that includes new stack, free stack, and translate address. This library is surgically integrated into the existing stack track library, which previously used libc malloc for stack allocation. With that, Lexa now supports multi-shell resumptions. The last piece of work in this talk is called Zero Lexa. With Zero Lexa, we explore a very different design trade-off. When compared to the traditional handler semantics, the lexical handler semantics has a performance disadvantage in that every function needs to be explicitly receive handler arguments. The passing and receiving of extra arguments impose a runtime cost even for really raised effects, such as exception. And we're concerned that even though lexical handlers have nice theoretical properties, language designers might still shy away from adopting them because of this overhead. Generation of language designers have advocated for zero overhead principle for exception handlers. This idea is best described by the quote from Bjorn Stroutrap: "What you don't use, you don't pay for." Zero Lexa is our attempt of achieving this goal, making Lexa the first language to have zero overhead lexical effect handlers. In the next few slides, I will demonstrate the technique by walking over 2 examples. We will first see a non-zero overhead execution, which is the state of the world now, and then we will figure out how to make the execution zero overhead. Here's the first example. I show the program on the left and a stack diagram on the right. Please only pay attention to the diagram on the right. Now, as the program runs, the function main installs a handler which is given address 5. Next, it calls foo by instantiating foo's handler parameter with this handler. The black box denotes a handler parameter binder, and the arrow denotes a parameter instantiation. Inside function foo, it installs another handler, which is given address 6. It then calls bar by instantiating its 2 handler parameters. Finally, bar raised 2 handler at address 5, which transfer control to the stack at address 5. Similar things happens when bar raised 2 handler at address 6. Now let's ask ourselves, can we locate the intended handler without passing down addresses? The key observation is that the handler provenance, which are represented by the arrows, are known statically. Even if we don't explicitly pass down the addresses, we still have a way to know where the handler passing originates. We can just trace back the static provenance information and find the intended handler. Let's see in action how handlers are located in zero Lexa. When an effect is raised, the control goes to a runtime stack worker. The stack worker carries a state called clue, which is a single integer denoting the de Bruijn index of the handler variable responsible for the raised effect. In this example, the clue is initialized to 0, which is the de Bruijn index of the handler parameter h2. The stack worker walks up the stack. At each call site, it transitions the clue according to how the handler parameter is instantiated. In this case, h2 was instantiated by the local handler inside foo. Since this local handler's de Bruijn index is 0, the clue is updated to 0. Finally, while still inside foo, the stack worker finds the local handler with de Bruijn index 0. It thus successfully finds the handler. Oftentimes, works about effects and handlers becomes challenging when it comes to higher order functions. However, zero Lexa also works with higher order functions. Similar to the first example, this example also has 3 functions: main, foo, and bar. Notice that the bar is a first-class function that is defined inside the scope of 2 handlers. And also notice that foo is a higher order function that takes in an alpha and a g, where alpha stands for the effects of that g raises. There are 2 call sites in the example. At the call site of foo, the alpha is instantiated with 2 handlers representing the effects the function argument bar can raise. Let's see what happens when we execute the raise expression from the function bar. We start stack walking with an initial clue infinity. We use infinity to denote the fact that the handler variable log is bound outside the scope of bar. From another perspective, log is captured by the function bar. Furthermore, the clue contains an extra field to record effect name. This extra information will be used to disambiguate a fork on the provenance path, which can already be seen on the diagram. When the stack walk arrives at the call site bar, it replaced the alpha in the clue with 0, which is the de Bruijn index of the effect variable alpha. To see why this makes sense, remember that an infinity clue refers to a handler captured by the bar, and alpha represents exactly the set of handlers captured by the bar. So it's sound to attribute the effect to alpha now. Next, the stack worker reached the next call site. De Bruijn index 0 indicates that effect is attributed to alpha, but alpha is instantiated with 2 handler variables. The second field of the clue now plays a role to disambiguate this fork. Because the variable log has a matching effect name logging, this variable is chosen, and the clue is updated to carry the de Bruijn index of the log, which is 0. Finally, the stack worker finds the local handler with the Brown index 0 inside main, and with that, we've successfully located the target handler. Zero Lexa works by compiling a source language where handlers' variables are passed as function arguments into a target language where each call set is annotated with metadata. This metadata records how the handler parameters would have been instantiated. These call set metadata entries are stored in the data segment of the binary and can be looked up using the return address of the corresponding call set. Importantly, Zero Lexa doesn't require any extra code to be instrumented into the binary. The stack work only consults the metadata when an effect is raised, so the cost is entirely off the mainline execution path. To integrate Zero Lexa into Lexa compiler, we modify the compiler to emit the type-directed call set metadata into the binary and implement the stack work routine as shown by the diagram. We've now seen 3 different techniques for compiling lexical effect handlers, each making distinct trade-offs. Direct Lexa is the most efficient, but lacks support for multi-shot resumption. Multi-Lexa brings back multi-shot resumption, but introduces overhead due to pointer redirection. Zero Lexa eliminates overhead for having the handler in a lexical scope, adhering the zero overhead principle, but raising an effect becomes more expensive. Furthermore, all techniques are formally proved correct, and you can find more details in the paper. In conclusion, I've represented 3 pieces of our work that hopefully will make lexical effect handlers more attractive to both language designers and compiler writers. I hope future languages will see lexical effect handlers as a compelling choice for control operators, and hopefully help reinforce a future of modular and performance software. Thank you, everyone. Thank you.